Hi everyone, my name is Michael and I work in a company called Hibernating Rhinos. Yeah, weird name for a company. We are specializing in databases and we are creating ORM profilers for an Hibernate and entity framework. Thank you. And our main product, however, is a NoSQL database called RavenDB. Maybe you've heard about it. And I'm a senior developer working on a core team of RavenDB, doing algorithmics and distributed stuff. And today we will going to talk about Raft, which is a algorithm, to be more exact, consensus algorithm. I've implemented from scratch the first versions of Raft for our database, and some things that I'm going to say is from this paper. From this research paper, everything has started about Raft. And some things are lessons learned that I and me personally and my colleagues learned from running Raft in production. We have clients that are running Raft for a couple of years now. And we've seen lots of issues, lots of interesting things happen with this. So what is Raft? And what the hell is a consensus? Previously, just 10 seconds of history. It's a family of algorithms. That's this definition you will see if you take a look at academic stuff. This family of algorithms is meant to replicate a state machine in a distributed environment. But let's leave these fancy words. I usually dislike reading too much academic stuff because they use too much fancy words and that go around meaning. So what the hell is a consensus? Before we talk about the algorithm itself, we need to understand what is a consensus. When we have client-server application, we do some operation like write 8, and the server writes 8. Okay, but what if we have a cluster of servers, several machines that if we write 8 to one of them, the rest, we want them to know that something happened to one of them, right? So the process with which all the servers somehow know that something has happened to one of them or to some more of them is called a consensus, which essentially fits the dictionary definition that a group reaches a conclusion or agrees on something based on what majority of the group thinks. But that was a bit abstract, so let's try a little example. Imagine that we have 3 bank accounts in 3 different cities on 3 different servers. And we want to transfer some funds from accounts, right? So we conceptually do this like this. We take from account A and add to account B. Then we take from C and add to A, and then we take from A and add to B, right? Sounds reasonable, sounds not very complicated, right? It's just RPC calls between servers if you think about it. But things are little more, when you go to real world applications, things are a little bit more difficult. By the way, if you have a question, you can just interrupt me and we can have a little discussion. If the answer is too long, you can ask it after the talk. But if it's something small, like I will answer it on the way, so don't hesitate to interrupt me and ask questions. And now I will ask you a question. What do you think can go wrong with this kind of exchange between servers? Anyone? No? What? Communication down, right. Something else? Data what was? I didn't hear? Data override. So this means if, for example, if we have several transactions going and they have conflicting things, right? That's what you mean. Okay. And there is another thing. For example, what happens if HTTP protocol does not guarantee in order, so things can get delayed? What happens if those transactions go out of order, right? So we first do the second operation, then first one, right? Or because it's not an atomic transaction, so we have multiple operations. What happens if we do it out of order, right? So that's kind of a problem because some accounts can go into overdraft and stuff like that. So what do we want out of a distributed system in general, right? So ideal distributed system should not be faulty, at least try not to be faulty, because servers can and will fail, right? And anything that goes hardware, software problems, network issues, stuff like that will sooner or later fail. Then we want to know who is the source of truth each time that we do something on a distributed system. What do I mean by source of truth? The data overwrite issue, when we have conflicting operations. Think about it like this. If you have a cluster of databases, right? I'm a bit biased. I deal with databases. So if you have a cluster of databases that replicate one to another, right? And you make a change to the same record in the same time, from two different sources, which one of them is correct? You cannot know, right? If you create a distributed system. So we need a way to determine who wins, quote unquote. So it's usually called the source of truth. Now, usually we want also to agree on the chronology, the order of events that happen, that affect the whole cluster. For example, again, I have example from databases. Let's think about topology, right? We have a cluster that has a topology. Now we want to add another node to the cluster, right? And we remove a node, add one node, remove another node. So the order of those events is important. We want all other nodes to know that we added something and then remove it, not the other way around, right? Because they may try to write to that node that was removed or something like that. So the order. So we want to somehow to know what is the order of events that happen cluster-wide, right? And then we want obviously that sometimes the faults, the errors are inevitable. For example, hardware failure. Sooner or later, for example, storage will fail. So sooner or later things will fail, and we want a distributed system to be able to recover from such errors, right? So this is seemingly very complicated task, but this is actually a lie. It's not the easy way, because distributed systems, when you deal with distributed systems, nothing is really easy, but consensus algorithms like Raft will make things simpler. So what the heck is Raft? Seriously, I've talked about what it is. You can think about it as a persistent event log. The whole academic terminology is nice, but it all boils down in practice. It all boils down to an event log that is persisted, where you care about the order of events. So essentially, everything that is related to Raft, you are managing a sequence of events, and you make sure that your whole cluster, your whole system, distributed system, agrees on certain order of certain events, right? But what is an event? It sounds a bit abstract. So events is something that affects your cluster. For example, think about robot swarms or drones, if you have several drones. So they need to communicate in some way, right? So and each decision of each robot, think about robots that play football, for example. You know, I'm sure you have seen at some point such videos. They need to communicate, and they need to know what happens to all of them at what every one of them sees, right? So this is something that is called state or state machine or event log, and you want to, again, academic thing, replicate the event log. This means you want to distribute whatever what other robots see to every one of such, let's say, units of the swarm, right? Think about load balancing. If you have a group of servers and you want some client to have to know which server is less balanced and redirect input to the less loaded server, right? So you need to have all your nodes in your cluster. You want them to know that what is the load on each server. So that's an event that I have sudden influx of input, stuff like that. That's an event that for Raft to replicate. And I mentioned before, that's another example, cluster management. So you want all nodes in your cluster to know that something changed in your topology, right? So this is not the only things you can use Raft for, and Raft is used for. That's just an example, so it won't be too much abstract. So let's take a look at actually how Raft works. Raft may sound bombastic, and if you take a look at a PhD and in general, if you take a look at the literature that deals with consensus algorithms and distributed systems, it may sound complex, but Raft was designed from the get-go to be simple and understandable, as they say in the title. It is, as you will see now, it is pretty understandable. So at first, we declare single source of truth, leader, and the rest are followers. We denote them with F. So all input goes through a leader, nothing else. Leader dictates what is the truth, basically, right? So the client says to the leader, take A and increment it by 10, right? Leader says, okay, I append this to a log. To my log, I append. Okay. There is two kinds of operations dealing with data Raft can do. Append, which is kind of the piece of data is approved by cluster, but not committed, not permanently written in the cluster, right? So the leader says, okay, to its follower, okay, append this operation, A plus equals 10, right? And the followers, they each return acknowledgement that, okay, I got this operation. And only if leader gets more than half of approvals or acknowledgements of its followers that they appended this operation, it can be considered as committed. This is called a quorum, and here comes the consensus part. When more than half of the followers approve this operation by appending it, it means that there is a quorum for this operation or Raft command. Sometimes it's called Raft command. And then leader says, okay, I have a quorum for this appending, so I can commit it, and sends the commit command. That's the second type of message leader can send to its followers. And then it is permanently written in the event log, right? And notice that the followers didn't return the commit. The operation, okay, this means that the cluster approved of this operation and committed it, returns to the client before. Why? Because even if the operation is committed, and this means approved by majority of the cluster, even if followers go offline, then go online, leader will still send to them this operation. That's the idea of a consensus, that once the consensus is reached, the leader, which is a source of the truth, right, will make sure that this event will get written onto its followers. That's nice, but did we choose the leader randomly? This is the second part of Raft algorithm. How the leader gets chosen via the cluster. And this is why I called it democracy in the cloud, because it gets done by having an election, believe it or not. So each node in Raft cluster can have three possible states: leader, candidate, and follower, right? And you can think about it like this, that each state has its set of behaviors it can possibly have. So what happens initially when you create a new Raft cluster from scratch? All nodes begin as followers, and after some time, node declares election. One or more nodes. Let's take we will be talking now about a simple case. Declares an election and asks for votes, right? That's the pattern of a candidate. The candidate votes for himself, and asks for votes, and the followers will vote for the first vote request that they receive, right? It's not exactly a democracy, has less politics. And then they receive, and this is also called a quorum. The candidate that has more than half of the votes will be elected a leader, and it's called a leader quorum. Leader election has a quorum. The leader has a quorum. And then it starts sending heartbeats. I'm alive here. What happens next is that followers have an election timeout. That's how it's called. Each time a follower receives a I'm alive message, it resets the timeout, right? So essentially, as long as the leader is alive, the followers won't declare an election, basically, or they can communicate with the leader. Now, if you don't have a quorum, this means that you have offline more than half of nodes, you can have no election, basically, because the follower will decrease the election, vote for itself, but it won't receive enough votes to be called the leader, right? So this is something that we should remember if we are thinking about any implementation of Raft protocols. You should have, ideally, you should have 3 or 5 or odd number of nodes in a cluster. Otherwise, you can have very interesting things, and some Raft implementations do not support even numbers of nodes. They require some tricks. For example, one of the databases, I won't name their names, require a virtual node to be run as an extra Raft node to have, if you have even number of databases in a cluster, you need to run another virtual node to have a quorum, not RavenDB, but some other database. I won't name names. And some Raft implementations like ours support this kind of thing, but that's another. If you're curious, I can talk about it after the talk. So what happens when there is issues? But first, let's talk about something. Leader says everything is okay, and what happens when there is network partition, or sometimes it's called split branch scenario? That's one of the things that we were talking about. What happens when there is network issues? So leader will try to communicate and get timeouts. So heartbeats will get timeouts. What will happen in the other side that can communicate, there will be an election, essentially. Because the other follower can vote for itself, another node can vote for it, so it can have a quorum and can have an election. Now notice term 1 and 2. What we are doing here, we are assigning a term for leader. This means each time a leader gets elected, it will get a version, quote unquote, or a term number that will always increment. This means that over the lifetime of a Raft cluster. This means that when the network partition heals, and we have 2 leaders, so how do we decide which leader is the correct one, right? So first time the leader with the largest or highest term sends a heartbeat, the other leader will step down. And the followers, when followers of a leader with a higher term will disregard or ignore heartbeats or any other messages like append messages from an old leader before it steps down, right? So in this way, we provide two things. We provide reliability for things like network issues, and we provide, or this can be, for example, leader goes offline then online, so we provide fault tolerance and reliability for network issues. And we provide error recovery, so if something was wrong and leaders goes offline and online, things will continue to work eventually, because obviously election is not something that happens instantly. It will obviously take time. So what happens after leader steps down? This is another interesting part. We had a leader, right? And it falls down, its server crashes and burns or whatever. And we have a new leader now, right? The new leader starts to, it starts to send append entries, to its followers. And it will do something very interesting. As you can remember, we have two types of entries in the event log, in the Raft event log. We have committed entries and append entries. And when the new leader sees that there are different append entries in its followers, it will override them. In this way, we always have a way to make sure that new leader or any leader is a single source of truth. This means there is no conflicting eventually. Again, obviously this process is not an instantaneous one, but eventually this is the way to make sure that there is no conflicting data in the cluster, in the Raft cluster, right? So let's talk a little bit about invariants, because they are important, and now you may see better why this kind of algorithm work and should work, because those invariants need to be upheld in order for the processes that I described to work. First process, it may be a bit obvious, but still it must be mentioned that each message or RPC that goes between the nodes of the Raft cluster needs to happen exactly once, and must have request and response. This means that even if there is timeout or whatever, it needs to happen with the code of a Raft implementation. Otherwise, things will go south, basically. Also, network may drop or duplicate packets and stuff like that. It should not also happen, and it dictates essentially, it restricts ways of implementing Raft. So things like UDP, for example, is not a suitable transport protocol for Raft messages between Raft nodes. Okay. Now, another thing, that each event in the event log should have a unique term and index. Index is just like index in the array, just incrementing number. And we must uphold that each entry has unique combination of those. And if this is not upheld, we cannot compare when, for example, leader goes down and another goes up. We cannot compare Raft logs between nodes. Because this is because this invariant, we can be sure that if certain log entry has the same term and index, we can be sure that the same log entry, basically. And another thing, index must be more than 0, because because serialization, stuff like that. So it's a good practice to have index greater than 0. Now, another invariant, comparison who has the bigger. In order not to overwrite data or drop things, we need to decide, for example, if you have two candidates, which one of them has a bigger log. Why? Because the bigger committed log, to be more exact, because committed events are guaranteed, Raft events are guaranteed to be the same on all nodes by the protocol, by the algorithm. So we want a candidate to win that has more complete information, obviously. That is why when there is a tie, this is one of the tiebreakers. Another one would be to hold another round of elections, but that is implementation detail, how this thing goes. Now, there are several gotchas that, in my experience, those gotchas are common to both if you want to implement Raft or if you want to use the third-party Raft. That this means you should check for those things and test the third-party implementation, because this kind of thing, everyone makes mistakes. It's not a matter of bad code or bad planning or bad whatever. It means that distributed system has lots of tight corners that may be missed when you implement this. So first of things that are issues or maybe possible issue in Raft implementation, race condition. Because we have a set of different behaviors, follower, candidate, and the leader, the state transitions is the weak point in many implementation, or potential weak point. And the sending of the messages, again, it's a weak point because sometimes there may be edge cases when this invariant may be broken. Now, edge cases, as I mentioned, it's not just race conditions for the state changes. It can be what happens when you have only one node in Raft cluster. What happens when you have even amount of nodes? What happens when there is an election and just the candidate goes offline? What happens on all those things that are just happened together with some other thing in the protocol? And those things should be tested both if you want to use some library, some database, some whatever messaging library that uses Raft, or if you want to implement your own. Breaking invariants, obviously, you should take care of not to break invariants because bad things will happen. And from experience, I can tell bad things will happen. You will have invalid and conflicting things, and you will have less hair on your head because you will pull your hair out trying to solve and debug things. And then there is performance issues. Think about it like this. Raft algorithm can work nicely in most implementations in the ideal condition. But what happens if you have very, very slow network with several hundred milliseconds latencies? What happens if you have a slow storage and you have influx of, I don't know, 1,000 Raft events per second? Sudden peak, something like this goes. What happens then? Maybe there is timeout. Maybe the election timeout will go out, and there will be something happens. So this thing should be noticeably changed. You should test for that. About performance issues, this is something that should be noted also. If you don't go with this rule of thumb, this means that election timeout should be less than average amount of issues that you have on your servers that may prevent communication, or, for example, 100% CPU utilization and things stall. So you should have election timeout much higher than your network latency. If your Raft implementation does not uphold this, you will have many too much elections and things slow to a crawl, so Raft won't be useful. Now, this is something very nice when not to use Raft, because Raft, both implementing and using it if you decide to use some third-party implementation for your project, this is an overhead and it may introduce some issues, both debugging, DevOps. It's an overhead, and sometimes you need Raft, or you can benefit from using Raft, and sometimes there is no point. So when you don't care about order of events, for example, think about caching, distributed caching. Do you care that some entry in the cache went into one server or another? You don't care about caching. The events are there is no point in tracking the sequence of events in a caching cluster, right? So caching no caching cluster won't benefit, I think, from Raft implementation. And when you don't care about things like fault tolerance, again, think about caching. So what if a server of caching server is unavailable for a minute? It's not the end of the world, right? So again, not all use cases require or will benefit from Raft. So in general, Raft is a very nice thing that can help you to know the order of events, and that's the reason that I hope I pronounce it right. The reason for existence of Raft, this means that you want to know the order of certain events that affect the whole cluster, be it commands, RPCs, or logging, or whatever. And it can provide you with fault tolerance and error recovery if implemented properly, and if done right, it will be amazing as a fault tolerance and error recovery thing for your distributed system. And that's about it. You can take a look at our GitHub repository. Our database is open source, so if you are curious, you can take a look at the source code of our database as well. We have a working Raft implementation at C#. So Java guys, don't throw eggs at me. But on a more serious note, is a battle-proven implementation. We have all sorts of tricks and stuff that we added to an original specification. It's not exactly a specification. It's more of a research paper that has guidelines on how to implement this protocol. So if you take a look at Diego's original paper, you will see all sorts of descriptions how it works, but the dry paper itself does not deal with enough resolution with issues and implementation gotchas I mentioned. So if you are curious or want to take a look at the working implementation or after, you can do it with this path in a GitHub repository. And if you have questions, you can ask them now, ask them later. That's my email. And I have a couple of books. I forgot to bring them from my room at the hotel. I have a couple of RavenDB books. So people who ask, first 3 people who have questions will get books, RavenDB books, just because I can. So, yes, question. This depends on implementation. We use kind of a gossip protocol, but again, it's the original paper assumes that nodes know each other and can address each other with RPC calls, remote procedure calls. So it's up to an implementation. It shouldn't. In general, I can't speak for all implementations. What we do is during an election, the cluster is read-only because there is no leader to accept the input, right? And if we try to, you can either try to wait for an election with timeout, of course, or just return cluster cannot accept write commands, stuff like that. So the idea here that if you don't have a leader, you cannot accept input. So the cluster will be read-only. Up to implementation. The client knows what we do. We redirect what we do, we can address any of the nodes, and if the node is not a leader, the node will redirect the call to a leader automatically, because all nodes know who is the leader, obviously. So because if it can't have a quorum, it cannot commit, and it will do only an append, won't receive a quorum, and what we do in our implementation is just time out and say can't do anything. That's what I wanted to.